I'm also very grateful to the organizers for putting on this nice conference and this nice program. I know that this is a lot of work, and I'm very grateful that I'm allowed to enjoy this. So I will talk about Lyman-alpha. As you all know, Lyman-alpha is a resonant line and therefore very sensitive to neutral hydrogen. And this is a good thing and a bad thing at the same time. It means that you have a very sensitive probe of neutral hydrogen, but very easily the optical depths are getting very large, what makes the treatment and the modeling quite difficult. So ever since the first quasars were discovered, there was a paper out very quickly by James Gunn, who predicted that the quasar spectra should actually be fully absorbed if the IgM would be neutral for any reasonable parameters. And this is sort of putting this here as a small formula. The optical depths for fully neutral hydrogen at a redshift of 3 at mean density would be 10 to the 5. At redshift 6, it would also be something like 10 to the 4. We can see this very easily in these nice spectra. The Lyman-alpha forest gets thicker and thicker, and for 2 decades now we have these nice spectra well into the epoch of reionization beyond redshift 6, meanwhile up to a redshift of well beyond 7. So you see here the absorption by Lyman-alpha on the left side, and you also see these beautiful near zones or proximity zones from the quasars that had been predicted earlier but were very difficult to see in smaller redshift quasars. So next I want to show this very nice compilation by Lawson, where he sort of shows how the transmissivity evolves at different redshifts as a function of the wavelengths relative to the rest frame wavelengths. So on the left-hand side, you see how the Lyman-alpha forest thickens just by becoming more neutral as you go to higher redshift. So this is the IgM, then a bit closer to the rest frame wavelengths, you will have the CGM, where the modeling is a bit more complicated. Basically, it's higher density, and therefore the transition goes down. And then in a very insightful paper that Jody Miralda wrote in 1998, he pointed out that you actually should see a red damping ring that goes well beyond the rest frame Lyman-alpha wavelengths, and this is something what we see now very frequently in the spectra, and is a very good signature of neutral hydrogen. I think there's one thing is that there's the overall evolution, that the Lyman-alpha forest becomes more neutral as you go to higher redshift, and eventually you see something like a Gunn-Peterson trough. I think what took a bit longer to realize, and I think the one who really made this point very strongly when he came as a Kavli fellow to us in Cambridge, is this the large variations that you see from line of sight to line of sight. So this is from a paper in 2015, 10 years ago, where George shows 2 spectra, where in one you still have a lot of transmission, many transmission spikes, and the other one is completely absorbed. Completely absorbed doesn't necessarily mean that the gas is neutral, as I just shown, but what's really remarkable is the scales over which these differences are, 160 megaparsec. Over these scales, I think the universe should actually, sort of in terms of density, already pretty smooth, so there must be something else going on. And what else going on is that we actually already had these spectra that told us that reionization ends about at that time, and that some regions are much more neutral than others. And I think meanwhile we're quite sure that at these redshifts, at a redshift of 5.5, there exist still some neutral islands left, and we see sort of the tail end of reionization just in front of our eyes in these beautiful spectra. So George quantified this by looking at the cumulative optical depth distribution, which is basically tau effective is just e to the minus tau effective is a mean flux. And he compared this to simulations that are fully ionized. These are the lines here. And as you go to higher and higher redshift, distribution becomes suddenly much broader. And this is a clear indication of these neutral islands still being present, as we found out afterwards when we could actually model this somewhat better. I think we had a beautiful review by Benedetta about the kind of simulations. So if I want to go into the Benedetta classification here with the simulations that we have run, so this is sort of in the class of large simulations. It's done in post-processing. And this is sort of the sweet spot if you want to do the Lyman-alpha forest data. It's large enough boxes to actually get the individual ionized regions into the box, and on the other side you have still high enough resolution that you marginally resolve the sinks of ionizing radiation. And this is sort of about the biggest dynamic range that you can go in one go. And I completely agree with Benedetta. You really, in this problem, the dynamic range is so huge that you have to change your kind of technique and adapt it to the problem that you want to do. So I think we convinced ourselves that with these spectra, you actually see the end stages of reionization. So we had here an older model on the top, where you see from left to right how things are already completely ionized at redshift 6. And in the models that actually fit the flux distribution well, you have these remaining neutral islands, the last bits of the overlap of the ionized regions. And we can really see this and study this in front of our eyes at lower redshifts than we actually had anticipated. I think once we had the simulations that reproduced it that well, I think this went into a large observing proposal about which Valentina will talk later, that was led by her and Sarah Bosman, and where we put actually in that we could already, with the older data, get not only the mean flux evolution right, but got the scatter right as well. So this is here a sequence of different redshifts for the effective optical depth distribution. And the level of fidelity with which you can reproduce this is actually quite amazing. So this led to this large program Valentina will discuss in quite some detail, where we looked at a number of statistics with a large team and more or less showed that they all agree with these kind of models. And one of the two questions that I want to discuss in the remaining time is sort of what are actually the sources of reionization. And we had seen also in Benedetta's review sort of the prime contenders are massive stars, maybe primarily in faint galaxies. It's not quite obvious, but it could also be still a significant contributions from what's called QSOs, or what we maybe now want more to call faint AGN, that are now found in large numbers. QSOs as sources of ionizing photons driving reionization have sort of come and gone several times, and Piero has always been on the side, Piero Madau, of pushing for QSOs. And one of the reasons why QSOs are problematic and completely being responsible for hydrogen ionization is that for normal assumptions about the spectrum of the QSOs, they would ionize helium not only to the first ionizing state, but also to the second ionizing state, and this leads to an extra heat input. We can meanwhile use this Lyman-alpha force spectra to measure the temperature of the IgM quite well. So this is an old plot here. This has improved since quite a bit too. And if QSOs ionize, they easily ionize the helium, what is responsible for the second bump here. So models with QSOs struggle with this. And we will later have a talk by a graduate student of mine, Shikha Astana, who looks a little bit on how much of that you can have. As I said, we had the first day full of talks about supermassive black holes, or at least massive black holes at high redshift, now being in large abundance in the samples. I think one early paper of this, pushing this point, was this paper by Harikhan et al., who basically claimed that 1% of the sources might be driven by AGN, and that might just be enough to sort of make more or less all of the ionizing radiations that you need to make the Lyman-alpha forest as we see it. There has been recently a number of papers that have started to look at this. I think Piero had a very nice paper out in a month ago or so, where he discussed what you have to do to the harder photons to maybe still come away with the quasars only driving the hydrogen reionization. Here was another paper led by Andrea Grazian, where he tried to convince us that there are actually enough quasars to do this. And you will later hear the talk by Shikha, where he shows us new results that are not yet published. The next point I want to be discussing is a bit another probe of how neutral the gas is and how to push it to higher redshift. And this is looking at Lyman-alpha emitters. And we have seen this amazing spectrum shown also on the first day of a Lyman-alpha emitter at redshift 13. And this is really puzzling because, as I said, with this high optical depth, you really need a reasonably large ionized region already at redshift 13 for this line to escape all the way to us. So for this reason, Schicker, in another paper that he has published earlier this year, has run a few models that ionize a bit earlier just to sort of cater for the possibility of being able to model this. So redshift 13 in these light cones is here. And the model that we had sort of as our fiducial model, so you see there are hardly any regions yet that have a bubble that's large enough that the Lyman-alpha could come all the way to us. So we have here two other models that sort of start earlier to being able to model this in a bit more detail as the data comes in. So modeling the Lyman-alpha transmission to us is a complicated business. So there's, as I said, there's the intergalactic medium that comes into the way. There's a circumgalactic medium that comes into the way. And if you want to raise the damping wing, it really matters at what wavelength the intrinsic emission comes out as well. So if I intrinsically in the ISM already have a lot of scattering and can scatter to the red side of the wing, it sort of ironically becomes easier than to escape and reach the observer. And so you need to model the escape of the Lyman-alpha from these objects as well. And we had heard nice talks, one from Harley, for example, where we see that now these very high resolution simulations get to the stage where they can actually do realistically model the Lyman-alpha radiative transfer in these galaxies at high redshift. When you want to now think about what kind of bubbles you need for the Lyman-alpha emission to be able to come all the way to the observer, you have to sort of keep into mind, and this is a point that Nick Nadin sort of impressed on me on a meeting that Benedetta organized, I don't know, it's probably 10 years ago now, one of these MIAB meetings, is that these sources are actually very, very highly biased. So if you go to redshift 6, even relatively low mass halos, if they have a mass that they actually can host a galaxy, they are all very highly biased. So they're actually preferentially sitting in the regions where the ionized regions are. So it's not so straightforward as just taking a volume factor evolution to see where these ionized bubbles are. And I had thought that Dan Stark would talk a little bit about his work on how these Lyman-alpha emitters evolve as a function of redshift. But here's a very nice plot from his paper with Tang et al., where Dan is one of the co-authors, where they actually have looked how the fraction of strong Lyman-alpha emitters is decreasing as a function of redshift. And as I'm already getting the warning for having 0 minutes, I show you just this plot, how biased the regions are. So here's a plot of the fraction of ionized regions as a function of the mass of the halo for the different models. And they're sort of coming up in redshift much earlier as the volume fraction. And I will skip the one on the damped Lyman-alpha wings and go straight to the conclusions here. And we'll finish here.
Questions? Yes, Andrea.
Thank you, Marty, for the talk. Concerning the escape of Lyman-alpha from these high redshift galaxies, and clearly you showed that this is very hard, and you suggested perhaps that the mergers can have a role. What about the outflows?
No, the mergers and the outflows go together. I think it's not the merger itself that triggers the escape. It's the merger triggers a starburst. The starburst gives an outflow, and this basically clears a channel. The mergers get much more frequent. The star formation gets more bursty. This might be merger related. To do that quantitatively, I think we need much larger samples to do that actually well. But I would completely agree, it's the outflows that help to clear channel.
Thank you.
Okay, then we have 3 other questions. So let's start with Mark.
Well, you had You had to skip over it, so I'll give you a chance to go back to it about the damping wings. And your bullet there says detection of damping wings due to a fully neutral IgM is now ubiquitous, but not everyone interprets these damping wings as necessarily just an IgM effect. So I just wanted to see what you had to say about it.
So I think this was one of the things that got me most excited about the JWST results, is that there's a clear signal with redshift of that there's something what is absorbing and looks like a damping wing. I think immediately afterwards there came another paper that there also seems to be an increase in proximate delays in these systems. So this can be easily mistaken by actually having more neutral hydrogen in the galaxy itself. My view on this is that there's so much data now and so much large galaxy samples that you should be able to discriminate between the two. So you should be able to know which ones are the ones that have the DLAs by looking for metal lines and looking just at the samples, and you should be the ones that are less sampled. The signal is clearly there. As you go to higher redshifts, there's obviously a damping wing there, which might be a combination of there being more neutral hydrogen in these galaxies and the gas getting more neutral. But as there will be 10,000s of galaxies we can look at, where you can split the sample in all sorts of ways, I think it should be able to get the signal out. And at the end, we should have a very nice curve like this, which I also went over just from this, when we actually learn how to interpret these signals, when we study these galaxy samples in great detail.
So do you think that from an observational point of view, you mentioned, metal lines as a distinguishing characteristic, and I understand that, but it's also, that generally requires higher resolution spectroscopy than
Sure.
what we do to detect these damping wings with the low resolution prisms, and so it's going to be quite challenging, actually, I think.
It will be
These galaxies aren't bright.
It will be expensive. You will.
The galaxies, we're surprised how bright these galaxies are at high redshift, but they're not actually that bright if you're trying to measure higher resolution continuum spectra.
You might find other correlations between these proximate delays and emission lines that are easier to see. Yeah? So I'm normally not an advocate of machine learning, but I'm sure there are correlations between what you see in absorption in the interstellar medium and the emission lines that can be dug out. And as we are just learning the hard way, that the interstellar medium at the high redshift is somewhat different. In the end, it doesn't matter how you find it out. You don't even have to understand the physics. You just have to class them the right way. So I don't think this will be an easy journey. But I think the only competitor for doing this will be sort of doing this with 21 centimeter, and I would say there's still 5, possibly 10 years left to do this before them.
So let's go for 2 quick questions. So first Joe, then Harley, and then we go on.
Harley was first. Okay. So on the one hand, I agree with you that seeing a Lyman-alpha emitter at redshift 13 sort of has to be telling us something about reionization. But you also emphasize that it's a tricky line to model. I guess, in principle, Lyman-alpha escape is actually more complex than Lyman continuum escape because it's a resonant line, it scatters. On the other hand, you have H-alpha or Balmer lines. I guess my point is, should we be optimistic that we can actually use Lyman-alpha to constrain reionization, given that we're not optimistic about predicting Lyman continuum escape from first principles? What is your view?
I think I'm most optimistic about the damping wings. Lyman-alpha emitters, I think, will be very difficult, because when I just looked at the Tang et al. Paper, you already struggled to get the equivalent distribution unabsorbed. It's very different from what Dan had in his papers 10 years ago. So this will be done. I will be one of the people being involved in trying to do this. I think this will be very hard. I'm more optimistic about the damping wings. Predicting the Lyman-alpha escape, I think I'm skeptical about.
Thanks.
Okay, so very quickly, the last question by Harley.
This is also about the very high redshift Lyman-alpha mission. So you have new simulations that you're trying to start reionization history much earlier in order to get the Lyman-alpha out. But as you know, there's the constraint on tau at redshifts 15 to 30. So I'm curious whether or not the new simulations that have a higher ionized fraction at redshifts 13 and above are actually consistent with the constraint on tau.
You have the constraint on tau here on the left, just here. I think
but specifically at specifically in the interval 15 to 30, right? It's from CMB. It's like a
I have the benefit of being very close to Joseph Stasio, who is very much into CMB data. And he always reassures me that this is the thing that the CMB is worst at. And so he doesn't have a problem with the optical depths going up again. Maybe not up here to the yellow line, but here up to the red line, he certainly doesn't have a problem whatsoever. This is really not something what the CMB is very strong at. And then you should also keep in mind that these are 1 sigma error bars. Yeah? It's only this community that wants every model in the middle of a 1 sigma error bar. Typically, you are 1.5 sigma away from the central value. So I don't think you should be focused on the CMB tau. This is the one thing I'm not worried about.
Okay, great, thank you. Let's stop here the discussion. Let's thank Martin again for his talk.